What's up, YouTube? In this video, we're going to be looking at gRPC. What is gRPC? Why, who, when, all of those questions. We're also going to be looking at the architecture of gRPC. And to some extent, it's going to be kind of a bit of a deep dive towards the end of this video. And then the plan is to have additional videos specific to .NET C#, where we have getting started with gRPC, and then probably another video after that, a little more advanced. So today's video is mainly gRPC. This is completely independent of .NET, C#, whatever. It's just what is gRPC? Why do we have one? Who's using it? When did it start? Stuff like that. And as well as the underpinnings, the architecture of the gRPC infrastructure that gives us some of these benefits and why these things were thought about and things of that nature. So I think it'll be interesting for those of you who want to know or learn about gRPC independent of anything .NET. It's kind of like my WebSockets video before I went down the path of SignalR, because WebSockets is, or SignalR is built out of WebSockets, is built out of, on top of HTTP2. So is gRPC, by the way. So there are some similarities there, but other than that, so think of gRPC as an alternative or a competitor or some technology that you would use in addition to simultaneously along with REST. REST works for certain situations, but does not work for many situations. You can have REST-ish services. These are not REST in the sense of the true REST follows will say that's not REST, correct? Because REST almost is good for like CRUD operations for the most part. But there are many operations you have on your services that are not CRUD related, and rightly so, because services should not be presenting a CRUD surface. That's the whole point of having services, is to give more business applications or business surface or a business API. So it's very rare, at least in my experiences, to have a service that surfaces CRUD operations. And nonetheless, without going into that argument, REST has its place, but REST doesn't achieve a lot of things. And the fact that REST is built on top of a protocol and has certain sort of requirements, human readability, JSON or XML, these kind of things, is exactly why we have a gRPC. And I'll get into the details of that. At a very, very high level, gRPC's motivation was performance. So what does gRPC stand for? As you can see here on the slide, gRPC, which is an open source, high performance remote procedure call framework, stands for gRPC, remote procedure call. It's weird. They call it a recursive name or something. I don't really care. Whatever it is. gRPC, the G don't stand for Google, even though Google was instrumental in starting the project that was the precursor to gRPC called Stubby. We'll talk about that. The G apparently does not pertain to Google. Google was trying to make this open source and they didn't want their name associated with it. So I'm not sure why they had G then over there. Either ways, remote procedure calls are slightly different from RESTful or REST-based calls. While REST is more, as I said, CRUD operations, remote procedure calls are mainly suited for, at least from if you're trying to be very particular, you can use REST for anything you want, right? Anything remote. But then the REST people will say, but that's not REST. So it's REST-ish. It's kind of sort of REST. RPCs are remote procedure calls. This is pretty much anything you want to do, calling from one remote application to another remote application. We've had RPC capabilities before when I started my career in programming. We had DCOM, distributed COM, Corba, then came XML RPC, and I had believe it or not, I had built my own RPC capability using raw TCP back in the day, because we didn't have things like SOAP and REST and all that. And sockets were not available out of the box, in toolkits like HTTP client is. So you have to make your own socket. You had to make it, then from the socket have to make like an HTTP socket or an FTP, whatever socket. And so I had made my own protocol between client and server. And so I was able to do this remoting. I didn't call it remoting, but the idea was I could send messages across the wire to server side. And eventually we also took this to cross-platform, meaning this was in Delphi initially. And then we looked at started using C#.NET back in the day. And so to allow for a smoother transition from Delphi to .NET C#, we had to have the ability to communicate from our Delphi applications to the newer C# application and eventually kind of sunset the Delphi application. So anyway, the idea is that there are ways you can have remote procedure calls, but remote procedure calls essentially meant pretty much any calling methods, sending messages across, getting back return messages. gRPC stands for remote procedure calls. Some people could argue that REST and gRPC can both live together. I think that's true to some extent, but not because one is REST and one is gRPC, or one is RPC and one is REST. I think they may coexist because of the fact that you might have to support certain clients that are still wanting to use REST. But I think gRPC is sort of the future, all right? But I can see them very easily living kind of hand in hand or together in the same ecosystem. The genesis of gRPC started with a project called Stubby from Google. Google had this need for a common cross-platform remote procedure call framework that they needed to use within their own data centers and across their data centers, across their services. They needed something that was super fast, efficient, cross-platform, because having a common cross-platform framework or infrastructure gave them the ability to get benefits such as efficiencies of performance, security, as enhancements are made to this common framework. They saw these benefits across the board, behavior analysis, and things of that nature. A company like Google would benefit from. And so they created this project called Stubby. Simultaneously, there was another project called Speedy, which is also internal to Google at that time. But by this point, Speedy had become HTTP 2 and a standard proposed to IETF, and then eventually become a standard. And that was like about 2015. And so we had HTTP 2, and the Stubby folks were looking at what they were doing internally. Now, Stubby had some incredible features, but it was sort of proprietary. It depended very heavily on knowledge and understanding of Google's own internal infrastructure. It was not open source. It was not available. It was not ready for open source. And all the other benefits that they got internally. However, because of the HTTP 2 coming out and becoming standardized, the Stubby folks felt, you know what, maybe we should rethink our strategy here, use some of the benefits we're getting with HTTP 2 that we're not getting with Stubby, and then piggyback off of that and try and get the benefits of Stubby and HTTP 2 as this combined thing, and let's open source it and so on and so forth. The rest is history. I think in 2015, they proposed this new project called gRPC to the IETF, actually to the CNCF, which is the Cloud Native Computing Foundation project. And so that was like the incubation of gRPC. And then since then, in 2015, it was open sourced. And so, of course, it was the proposal and things of that nature. Now, this project, the CNCF project, is managed by Google and a bunch of other people from various companies who feel like they want to have a say or a stake in this idea of where this gRPC is going. And so you have pretty much most companies like Microsoft and Netflix and others participating in this project. It's an open source project, so of course you can have pull requests and things coming in. But there's something unique about this project, the way it's run. There are various toolkits that are for the different languages, like C# or Kotlin or Swift, Go, etc. All of those toolkits or libraries are managed by the project to ensure that gRPC is truly cross-platform. So they have a bunch of tests that they run internally to ensure that some library A, language A, can talk to a library B, and all of those tests pass, and then vice versa, and kind of the permutations of all of that. I think that's a really cool feature because that's not leaving it up to the library sort of maintainer, if you will, to ensure backward compatibility. The project itself is taking on the onus or the responsibility of saying, you know what, we are going to make sure these libraries are compatible. Cross-platform in terms of operating system, but also cross-platform in terms of languages, right? So I think that's a unique, cool feature of the gRPC or CNCF project because it's taking on more responsibility and forcing the powers that be, the people that build the libraries, to collaborate internally before they make that available to the public, right? So the public is dealing with some of the incompatibility issues, and that's not fair. So that's one change, I think. I don't know of any other project that has a similar way of operating. So one of the reasons, as we heard from Stubby's history, was to have this high performance, low latency infrastructure framework for remote procedure calls. And so if you have a need internally within your data centers, within your application and enterprise, where you need to talk to multiple services, using gRPC for those internal communications, I think is probably the first place to start if you're looking at using gRPC. Leave the sort of the public facing parts to REST and APIs. But for internal purposes, I would say you could use maybe within your own project. If you got a bunch of microservices within your own project, then your projects could start using gRPC within your own, amongst your own services, and then eventually across the enterprise and so on. I think that might be a good migration path for those of us who would like to use gRPC. Okay, so low latency, high performance, cross-platform, and portable, meaning mobile, PC, laptops, tablets, and IoT devices. So gRPC works across all of these things, and also low latency, lightweight, etc. There are a bunch of large companies or well-known companies using gRPC already. Of course, Google, since they started it. Netflix, Square. Square, by the way, I think also recently bought Tidal, the online music, like the Spotify competitor. In fact, Spotify is also using gRPC. They've been using it quite a while back. Spotify also had an internal competitor to Stubby called Hermes. Not a competitor, but they were all trying to do the same thing. They all wanted a super fast, low latency communication, RPC communication protocol that is not HTTP based and REST based. Maybe you should talk about what's the problem with the HTTP REST based stuff versus gRPC. We'll talk about that in the next couple of slides. If you haven't taken a look at my WebSockets video, Introduction to WebSockets, or that's whole signal hour thing, I'll put a link to it over here. I talk about HTTP2 there. I'm going to talk about some of it here as well. But essentially, think of TCP as a layer. And I've even talked about the OSI layers, so OSI stack in that video. I'm not going to go into the details here, but just for those of you who have not watched that yet, TCP is sort of at one layer. We call it an application layer, but it's the bottommost part of the sort of the application layer. What do you call the transport? In OSI stack, this is the transport layer. So TCP is used as a transport layer. Think of that as the surface of a highway. Just that, it's the fact that it's a road. And HTTP, well, so let's say land transport versus air and track and, water, ships. So think of TCP as land transport. And then you have HTTP or some protocol on top of TCP, such as HTTP, SMTP, POP3, and so on. So that's the sort of the surface, if you will, tarmac. This is a dirt road. So that's HTTP. Then we have something called a wire protocol. So there's a transport layer, and then there's the wire protocol. The wire protocol is so on this highway, you have different types of vehicles that can travel, from trucks to buses to cars, sedans, sports cars, SUVs, scooters, motorcycles, stuff like that. So think of the wire protocol to be the kind of vehicle going across and how that vehicle looks as it's moving on this highway, right? Actually, I'm going to use this metaphor as we go through this talk, but I think this highway metaphor works pretty well for this whole thing. So gRPC uses a protocol called protocol buffers, or protobufs for short. Protocol buffers is a few things. It is the encoding, a binary encoding format of packaging data and to send it across the wire. So it's the type of vehicle. Is it a bus? Is it a car? Is it a scooter? Is it a cycle? Is it a sports car? Whatever. The way that data is packaged and sent across the wire. So that is protocol buffers, or protobufs. But the other thing protocol buffers is the definition of your service, kind of like a WSDL, or like with Swashbuckle and others in the REST world. Having a means to describe your service, the schema of your service, the data inputs, outputs, and the different methods, if you will, available on your service. So Protobuf is also a service definition or interface definition language, and it's in a .proto file, something .proto file. And these are all standards, by the way. gRPC is not coupled to protocol buffs, or conversely, you can use protocol buffs for anything you want of your own. It doesn't have to be only used with or along with gRPC. You can use it for your own TCP communications. So it's independent in that sense. But when somebody says protocol buffs or protobufs, they're meaning a couple of things. The schema IDL, or we call it, the interface definition language, but also, which is a file, and we'll see that file, a sample of that file. But it's also the way data is packaged, if you will, the wire protocol, as we call it, the way that data is sent across the wire, and it is a binary format, right? It's language neutral, as you can see here on this slide here. It's language neutral, platform neutral protocol, and it is an extensible mechanism for serializing structured data. Now, that's not to say that you cannot serialize unstructured data. You can also serialize JSON if you wanted, but that's not the intent. It's intended to use structured data. By that I mean definitions of objects, DTOs, models, messages they call it. So a remote procedure sends messages to the remote server and gets back messages. We would call them models or DTOs. They're making it clear that its messages is not like object references. It's not like instances like DCOM and Corba literally propose that they shunted objects across the wire. I got your object in my application with the behavior. No, it wasn't just data. RPC was saying, well, let's not send objects across the wire, because they learned their lessons with DCOM and Corba, and they came up with RPC, and RPC basically was remote procedure call, send messages, get back messages. And that's what gRPC is trying to do as well, just stick to messages. And so that's the structured idea of structured messages. Let's look at the example of the Proto file, and then I'll also talk further about some things that you might want to be aware of. Don't need to have a full understanding of the Proto files today. When we go in the next video into building an application in C#.NET, probably be a better time to look at the in-depth version there. I'm going to highlight a few things here with regards to the Proto file. So first of all, we have this Proto version 3. There are ways in Proto files to import other Proto files where you might have definitions. In this case, the definition of a timestamp type is over here. I won't go into the details of that, but that's what the import statement is. So here's a message type. It's the book type. These are the fields in the message. There's an ISBN, a field called ISBN. It's of type int64. That's in C# long. And it takes the sort of the first position. Now these numbers play an important role in the Protobuf protocol. You can't change them once you've defined them. These are the data types available in protocol buffers. They are not C# types. These are protocol buffer types. And they support mainly the scalar values. You can have your own custom types as well as this one. This timestamp thing is over here. And there's another Proto file that uses it. This particularly does not use it. But the idea is that you can have specific types, your user-defined types. Then you have the sort of built-in types in Protobuf itself. These are typically the scalar types, the ints, floats. There's no decimal out of the box. There's no datetime, which is what the timestamp thing is. A bool is there, enums, things of that nature. But then you can also define your own, and you can share or use common libraries. Like Google has produced additional types like timestamp and things. You might want to use that. So that is the idea of a timestamp is commonly understood across everyone in your app company, rather than you having your own understanding of it. Don't want to go into details, but I want you to understand certain things here. So these are the three messages, meaning these are, think of them as the models or the DTOs, the data that goes in and out. So that's the model. And this is a book request, and this is a book by author request. And as you can see here, this is the service definition. And what it says over here is there's a method that's called a remote procedure called getBook. It takes in a book request as an input, and it returns the book as an output. That's what the next one is saying. It's get books by author. It takes a book by author request and returns a stream of books. Now let's explain these two things here. First of all, notice that there can only be one argument to a method. It could be a scalar type, or it could be like a model that you define, like the structure that you define. But only one. You can't have multiple. So that's one of the sort of features or limitations of gRPCs, that every method takes only one thing. That one thing could be comprised of one scalar property, or pretty much nested, any depth of nested classes, not classes, structures, we call it messages, as you'd like. So, but from a signature point of view, it takes this one thing, right? The one message. So, and it returns one message. It can't return multiple things, and it can't take in multiple things. And the recommendation is, even if you have a single scalar thing you need today, let's say in 62, 64, or in 32, you might want to wrap that up in a message so that tomorrow when you want to expand on it, you're not going to break. It's not going to be a breaking change. This structure, this Protobuf format schema does support extensibility and backward compatibility to some extent, with some caveats. We'll go into the details of that soon. The stream is, if you remember my video on C#8 streaming, I made a sort of series of videos there. C#8 streaming. This is the same idea here. So Protobuf supports the idea of streaming, which is it's not a collection of books. It's a continuous stream of books that are returned as part of the response. So gRPC supports streaming. We'll talk about that a little bit detail, but that's what this is implying here. That is the stream. They also have the notion of arrays. They call them repeats. There's another set of messages here. And you can see here that there's a person message. Now these numbers, again, I said, are specific. They have to be unique, and they cannot be changed once you assign this number to that field. It can't be modified later. And so here's a person that has, at the top, it has these three fields. The 4 is here. So this is a field on the same message person. It is of type phone number. And that phone number is another message nested inside of this message. So in C# that would translate to one class nested inside another. But that's what I'm trying to show you here. This is just another field. Like that's number 3. This is number 4. This is the type, and it's repeated, meaning it's an array. The 4 is not saying it's an array of 4. It's just saying that's the position 4, but it's an array. That's the repeated. And this timestamp comes from that namespace that we imported earlier. And that's another field. So last updated is a field. That's 4. That's 5. And the type is a timestamp. And this timestamp is coming from this included file here. So it's okay if you don't understand. Oh, and by the way, you can also put comments like this in the Protobuf. These comments, these style comments, double slashes and the slash asterisks are both supported in protocol .proto files. This is a .proto file. All right. So just a brief introduction to .proto file. I wanted you to see it so that you understand there's a file that's describing the schema, but is also used for tooling purposes, meaning these are machine readable files. At this point, we're going to talk about, I think the next slide here is performance. Yes. So let's talk about, just at a high level, why gRPC or RPC versus REST. REST and HTTP, specifically when REST was thought about, dreamt up. This was before like HTTP 0.9, right? Something like that. These protocols, HTTP, SMTP, POP3, FTP, these were all text-based protocols, which means, which is a cool thing. I mean, when I learned TCP/IP, I had a blast of a time checking my emails using Telnet, browsing websites using Telnet, actually typing out the protocol and looking at the response and typing out the protocol. It's the coolest thing. But all these protocols are text-based protocols. They're intended to be simple and human readable. Well, our desires, our requirements have changed. The internet is way too big and it's getting very, very busy, and we just need more speed. And so this text-based, human-readable, overly verbose protocols don't work anymore. So while REST is okay for certain situations, when you need truly high-speed, lightweight protocols, you can't use HTTP for the most part. HTTP the protocol has two parts to it. It's called like header, and then there's the body. The body is the data typically that you want to send across, and the header is communications that are going on, metadata, if you will, that goes on between the clients and the servers. All right. So with TCP protocols, even if you create your own, there's always some header metadata information because the other side has to know how much data you plan to send. And then when you're done, things of that nature. So that at the bare minimum, the receiving party, because of the way TCP works, needs to know how much data to expect or some way to tell if you've finished. So it knows that you've stopped transmitting. It's come to the end of the transmission, the data transmission. So what HTTP 2 and then therefore gRPC benefit from is the fact that HTTP is ubiquitous, as in it is available across literally the planet now. And people have a lot of infrastructure and investment in protocols, proxies, hardware, security infrastructure, all of that at the HTTP transport layer. So if anything that rides on top of HTTP, such as WebSockets, such as gRPC, will benefit from all that investment in infrastructure. So that's definitely a cool thing. Other than that, though, this human readable aspect, making extremely verbose things like XML, JSON, these are extremely verbose protocols. And so what if it's human readable? The problem is costing us. gRPC at the heart of it is binary serialization. Binary serializations always work out to be super, super small. So when you transmit that data across the wire, a very little amount of data is going across the wire. And that's what they needed internally in Google when they were doing this whole Stubby project. We could all benefit from it because even a little mobile application would benefit from transmitting less data across the wire. That's going to cost you less. It's going to be faster, use up less CPU resources to try and deserialize that data, to consume the data, less memory, and so on. So it's a win-win for everyone, for devices, for networks, for cost, and for the end users to see better performance. Everything sort of becomes faster. Now, because binary serialization, you can't see the data going across the wire. Right? So you're not going to get like a Postman. Well, there's a tool, but it's not Postman. You can't see the data. You can't type it in by hand as a dev or during the development cycle. Now, there are tools that support that feature, meaning if you can imagine these 2 points on the wire from here to here. When the data goes from here to there across the wire, that's in binary. Can't read it. But just before that, you could have a tool that kind of converts your thing to binary and sends it across the wire, right? So it's possible to do that, and there are tools that support that, and you can make your own if you want it. But I'm trying to get across that the binary serialization comes at probably a cost. That is, it could make things a little harder to debug. Wireshark, which is if you don't know what that tool is, it's like a sniffer, if you will, network sniffer. It can sniff data going across the network and tell you where connections are being made, TCP connections are being made and such. And there are, I think they're called dissectors or dissectors. I don't know, I would call them dissectors. They're like interceptors. They're dissecting the data that's going across the wire. And so there are dissectors for protobufs. So you can see data that's going across the wire. You can actually read it. It'll take the binary and sort of reconvert it back to something more human readable. The other thing is it's strongly typed. One of the issues with REST is anything text-based is like there's no way before you start sending the data that you get stopped. And you can send what the heck you want, and then you get stopped on the server saying, I don't know what you're saying. I don't understand what you're saying. Because these are strongly typed protocols, at compile time, at least for those languages that are strongly typed, at compile time, you're going to see the problem. At compile time, you're going to be told, hey, you can't make this call, that the type you're sending across is not correct. So strong typing, of course, gives us the benefits that we all love in C#. It's a strongly typed language as well. And so we understand the benefits of a strongly typed language. I won't go too much into that. HTTP to transport. gRPC is not dependent on HTTP in that sense. It is a pluggable protocol from a gRPC point of view. But today we have that implementation. And so in that sense, it depends on HTTP. It won't work on HTTP 1.1. It'll only work with HTTP 2. So of course, you have some constraints there in case you don't have infrastructure that supports HTTP 2 yet. One of the core reasons that HTTP 2 gets its benefit is from a feature in HTTP 2 called binary framing. So here's my highway metaphor again. Imagine you're watching a two-way multi-lane highway. Each side has multiple lanes. And this is like a highway, so maybe 4 to 6 lanes on each side, right? Two-way. Binary, and on a single lane, there are a bunch of cars or vehicles. They don't have to be cars. They could be like trucks and buses too, right? So there are a bunch of vehicles. Binary framing is the ability to, where each vehicle on this one lane, you are prioritizing and saying, okay, I know you're going in this fashion right now, but this car that's behind is going to end up being higher priority than this car that's currently in the front going that way. Binary framing is this packetization, or the framing as we call it, the packets, the vehicles, and the ability to define priority of these frames as the data is being sent across the wire. Most of HTTP 2's benefits come from that core functionality. From there, you get things like streaming, and you get things like multiplexing and stuff like that. So one of the benefits that gRPC gets because of HTTP 2 is the binary framing feature. Then there's something like multiplexing. Multiplexing this actually comes from electronics, at least I understand from electronics background, where, have you seen those digital clocks that have those segments, to form like an 8? And then there's a clock. So there's so many digits, but each digit is comprised of all these segments, the kind of, you know what I'm saying, right? When you look at it, you think it's all glowing simultaneously. But what happens really is every segment is lit up one after another. Sometimes it's every digit is displayed and it's multiplex, meaning you're only feeding power to one entire digit, but you multiplex it such that you're firing them here so quickly that it looks like they're all on. The human eye is not able to perceive that difference. In some cases, every segment in every digit is lit up independently, which is also happening, meaning it's both. It's the digit and the segment, both are being multiplexed. The idea being you can use the same pipe, if you will. Do the same thing with, optical fiber. It's the same fiber. Think of it like a glass pipe. And there's many people sharing that data, that pipe for data. So it's multiplexed. Each of us gets also a time slot, if you will. On the CPU side, it would be called multi-threading in some sense. Multiple threads are able to use the CPU, but the time share in some sense, right? So it's kind of like a time sharing mechanism. So that's multiplexing. Multiplexing is a feature of HTTP 2 that gRPC relies on because it requires that ability to have multiple conversations on the same. So imagine this highway, multi-lane highway, two-way highway. You can use your side of the highway with multiple lanes, and this multiple lanes is called multiplexing, meaning each lane is a different communication that's happening at the same time. So using the same channel, the channel is the highway itself, but multiplexing, allowing multiple conversations to be occurring simultaneously in one direction. And then it's also full duplex HTTP, which means both you and me can be talking at the same time without missing a beat. So you could be sending me multiple multiplexing conversations from this side, and I could be doing the same from that side. And we're both completely understanding each other, all happening together, right? So that's the benefit of HTTP 2, but gRPC relies on that. Another feature of HTTP 2 is header compression. So as I said, this HTTP protocol is comprised of a header part and a body part or content part. And headers can be small, but headers can also be fairly large. And this is metadata. And so header compression allows for the compression of the header part to send less data across the wire. We used to use gzip or zlib, gzip or zlib compression for HTTP back in the day. But then there was some form of a security attack on that gzip, whatever. And so then since then, we have used, I forget the name of this new compression technique. With the header compression, we're sending less data across the wire. So between header compression, multiplexing, and binary framing, gRPC is basically utilizing all of those features of HTTP2. So to some extent, it is dependent on it, but it's not in terms of the actual architecture. We'll dig a little bit about on that. Is just a pluggable architecture, the transport layer. By using HTTP2, we are getting 3 times, maybe in some cases more, benefit in terms of latencies and performance, and approximately 11 to 12 times less CPU utilization. In other words, the binary format is so small and simple to encode, decode. That's less taxing on CPU and memory on the hardware, and it's giving you huge amounts of benefits. Some cases 15 times faster network-wise, depending on how much data is going across the wire too, right? Another protocol that is currently in the works is part of HTTP 3, in fact, is called QUIC. QUIC. Some people say QUIC is an acronym. It stands for QUIC. QUIC UDP Internet Connections. QUIC. Again, this was a project that was internally started at Microsoft. These are different groups in Microsoft, each trying to solve a problem. This is more at that transport layer. So it's a much lower level than Stubby. Stubby was the precursor to HTTP2. Stubby was the precursor to gRPC. Anyway, QUIC is sort of now the HTTP 3 protocol. It was proposed to the IETF in Engineering Task Force in 2015. Anyway, it's becoming a standard. It has already become a standard, but now it's being ratified. This is the HTTP 3. So HTTP 3 and QUIC are kind of hand in hand. It uses UDP instead of TCP. So it's quite a bit different from HTTP 2 in that sense. Born out of a need within Google, again, to get better performance. And there's a problem with TCP, and especially in HTTP, called head-of-line blocking. Long story short, TCP is a connection-oriented protocol, and so if some data if the connection was dropped, you've lost that data. And if there's multiple pipes on the same connection, and if the connection severs, then everyone loses their data. So it's a bit of a problem for resiliency purposes. With UDP, which is a connection-less protocol, some of those issues can be solved. And so, anyway, the short of it is that gRPC can also be used with QUIC, which is a transport layer protocol. Again, because of this pluggability of things, gRPC could eventually start being used. And they've been doing some testing. So it's not tied to HTTP2, but currently that's what we have. Once we get HTTP 3, we'll have implementations of gRPC on HTTP 3. QUIC in itself is trying to replace TCP. Not even, it's not like HTTP, it's TCP. So it's that transport layer, while still being compatible to in many cases or in many senses to TCP, yet it's trying to make TCP obsolete, essentially. And it's nicknamed, this is a nickname, it's not going to be called that, but it's the nickname called TCP2. Like not V2, but /2, like HTTP/2. This is TCP/2. So that's the nickname for QUIC, because it's trying to replace the transport layer. Anyway, enough about the performance thing. Let's move on to the next slide. Okay, so here's the gRPC stack, or the architecture of the gRPC stack. There are different libraries, mainly gRPC C core, as you can see here, C core gRPC, C core. That's the C language core. And many other languages use the C core as its sort of underpinning foundational core. And then those languages have a wrapper on top of that through this API. The Surface provides an API, and that API is exposed to any language that wants to use the C core for its own purposes. And such languages like C++ and Python, Node.js, PHP, Ruby, etc. use that. Now we had or used to have used the same C core in .NET, but now in .NET, recent .NET versions, we have our own native implementation of gRPC. So whereas earlier versions of .NET relied on this library that wrapped around the C core, now this whole stack that you're seeing here, the gRPC stack, all of it is written in .NET Core. So we don't have reliance on the C core. But other languages do rely on the C core. And then there are some languages that have their own core. The Java core and the Go core and the Dart core. And now we have the .NET 5 core. So .NET 5 core, the core gRPC, which is built purely from or completely in .NET. And it's cross-platform and so on and so forth. So let's talk about the design of the stack. That might give you some insight into extensibility and the basic architecture. So the core is comprised of two parts. Let's call it the top part and the bottom part. The bottom part, the IO manager, is everything to do with hardware, transport. Every platform is totally different. This platform, the IO manager platform code base, is highly specific to every piece of hardware and every operating system and so on and so forth. So it's the one layer that is tightly coupled to the thing it's running on at that moment in time, be it a phone or a machine, and whether it's Linux or Unix or macOS or whatever operating system. This piece has got the code that is going to be tightly coupled to that implementation detail, right? From that point forward, it gets a little better. Then we have the transport. Okay, we are planning to use TCP, HTTP2 as our transport. So as I said, it's pluggable. You can remove that transport layer, swap it out, put another one in. So you want to go to QUIC, do that. I'm not saying it's simple, but it's built in that sense to be pluggable, replaceable and pluggable. The surface is essentially providing the API portion of it. So this is sort of the public surface of the gRPC core, and any language that doesn't want to build its own core can use the Surface API to build their wrapper. So I think for Kotlin, they build a wrapper around Java. So Kotlin is another language that's supported or uses gRPC. I don't know the implementation details, but I'm guessing since it's Java based that they would build a Kotlin wrapper around the Java core, Java's gRPC Java core. Then the filters is very much like middleware. If you have seen my video on ASP.NET Core middleware, I draw this whole pipeline. Okay, this is going vertical, same idea, horizontal, vertical. Requests come in and it goes through different parts, and you are able to intercept. You can intercept any traffic going back and forth by having an interceptor. So it has to come to you, comes to you, and then goes back out, comes back and goes back out, right? So I'm sort of intercepting the traffic. So I see the traffic going in, and then it comes back this way, and then I see it going back out and comes back this way. And I'm able to look at and change and modify what I need. Interceptor, middleware, they're all filters. So basically it's called filters, interceptors, middleware, one and the same thing, to give us features like monitoring, tracing, security, logging, all these kinds of things. Anything that has to happen, or that you would like, or you would like to modify, you can use filters as the extensibility point, if you will, at that level. So not at transport, not at IO, but at the sort of the application level, not your application, the gRPC application level. And so some things come out of the box with gRPC, like monitoring, latency, etc. But these are where you would extend that. gRPC supports different kinds of, I'm going to speed up here a bit. gRPC supports specific kinds of communications. The unary communication, meaning I make a request, you give me a response. I make a request, you give me a response. That's called the unary mode of communication. Then we have client-server streaming. So I make a request, and you're streaming data to me, and I just keep receiving data until you tell me you're done. So you're streaming data. It's not one response, it's a continuous stream. Similarly, client streaming, where the client is streaming data to the server instead of the server streaming to the client. And then bi-directional streaming, so both sides are streaming. Now, the general mechanism for making a connection, or when you want to communicate, goes like this. As you can see from the diagram here, you first open a connection and then you make a call. But when you make a call, it implies you are sending some initial metadata, then you're receiving that initial metadata from the party that you send the data to. So there's a sort of a handshake communication going on. Then you send the actual message. Then you receive a response to that message. And then you send a trailing metadata to let the party know that you're ending the conversation, if you will. And you receive the trailing metadata to get the confirmation. So when you make a call, that's what's sort of happening. Now, while this is happening, this metadata here is opaque to the protocol. It's like it's used in HTTP2 scenarios, it's used in the header. So it's not interfering with the data. In that sense, it's opaque to the protocol. The data is independent of the metadata. And you can send all kinds of information on the metadata as you want. Of course, both parties need to understand what that means. But of course, within the protocol itself, some metadata is exchanged as part of this exchange protocol. And we'll talk on the next slide now. Some other features we have. Oops, sorry, let me just go back. So the extensibility comes from those filters that I talked about. Yeah, filters, interceptors, middleware. Multiple transports can be supported by swapping out the transport layer. Authentication comes from the interceptors as well, tracing, monitoring, stats. Okay. Some of the other features in gRPC is error propagation. And if you don't like the error propagation mechanism, then you can use the metadata features. You can also customize. You can send your own metadata across. And that we can have servers talking back to the class, propagating additional information related to error propagation in case you find the built-in features not satisfactory. All right, so that's also possible. That's why I brought up the communication and the metadata exchange part, because that might play a key role in where you think about gRPC. You have things like auto reconnect. And the reconnection is an exponential backoff, if you know what that means. Basically, the idea is if I'm trying to connect to you and I can't connect, I'm going to try immediately. I'll back off. I'll try later. So maybe the first time I'll retry in 10 seconds, then I might try in 30 seconds, then I might try in a minute. I'm exponentially backing off. So I don't trying to kill your server. So it's all automatic, and it's also using exponential backoff as a mechanism for retries. Cancellation, timeout, and deadline. Sorry, cancellation, propagation, and deadline propagation. Cancellation is when, if you, as a client, let's say I'm calling you and you're calling somebody else, calling somebody else, calling somebody. There's a chain of calls that start from the client originating the call. And for whatever reason, I want to cancel the call because my user decided to do something else. If I send you that cancellation, you can propagate that downstream to all the other services you call. So all can stop doing what they're doing and not waste time doing something I don't ever need anymore, right? So that's the cancellation propagation. Deadline timeout is similar, but the idea is that I say, okay, I wanted to get me this information as a client. I'm talking to the server, but you got to get me this back in this much time. So I'm setting up a deadline. Like your manager tells you, you got to deliver this to me tomorrow. That's the deadline, your deadline. Similar idea. And it deadline propagates as well. So if, let's say, you have to call another party and I've given you, let's say, example, 10 seconds. It's going to take you 5 seconds. So at most, you got 5 seconds to give the other person to get the data they need to get to you so that you can do your bit for the 5 seconds, right? So you can propagate 5 seconds downstream from you and so on. The idea being that gets propagated so that it's not just known, by the one person, and there's no way to communicate for me to tell you that there's a deadline. And if you pass the deadline, you can just stop because I've already gone away. I can't wait around, so I've gone away. So no need for you to spend your time and effort continuing on only to find out, an hour later that I have left. Some of the other features that come out of the box as part of the metadata as well as the filter mechanisms is things like load balancing, and they have the standard load balancing, like the round robin and the first available. They've also introduced a new style of load balancing called look-aside load balancing. Essentially, so with load balancing, you have to know who is free. And so this look-aside is saying, okay, there's something else that's giving you this information about what servers are free here. So something else is updating this data here on another server. And so you could look here before you make the call. Just from making the call and then finding out you go back somewhere else. So that way, with one ear or one eye, I can figure out who to call, and then I make the call to the person directly. So I'm not going call here to be sent over there because that one is free. With load balancing, you go to one machine and then you're sent to another machine. So there's an extra hop there. with look aside, the idea is that these two can be happening independently, where I can determine who to call before I make the call. So it's not part of the request. It's two hops, but it's not part of this one request. I could be making this before I make that. A bit complicated. All right. Well, I was hoping to keep this really short, and I know I've been rambling on a bit. I'm going to try and cut out some of the stuff in the edit. So I don't know what all I can cut out, but I hope this has been fun, has been enjoyable, and I hope you've learned a few things. If you have, please give me a thumbs up, and I will see you next time.